Stanford University.
Sally, thank you for the invitation and introduction. Probably one thing to add after this talk, just two events right here. The better food is the GSEPS event. So if you taste out, the better food is upstairs, not the same floor. So you won't make mistake. Well, I think this is the right timing to give the whole community an update what's happening in the Bay Area Photovoltaic Consortium. We won this award last year. It's multiple people's effort. You know, Steve Aglash is sitting right here. John Banner might be somewhere in the audience also. And there's also really many people involved to bring this award into Stanford jointly with Berkeley. This award is under the DOE Sunshot Initiative. So this is a recent program led by Ramesh. Ramesh used to be a professor at Berkeley and stepped up to lead this initiative. It's trying to refocus the DOE's photovoltaic program, try to help the industry to reach $1 per watt in the installed system cost. Let me give you a little background. Why DOE wants to do this, and then how does that fit into the university research environment, how we can help the industry to do that at the same time fulfill the research and education purpose at university. This is the plot of the shipment of PV modules over the years. Very exciting thing is recently, look at in 2011, you are talking about more than 20 gigawatts of PV module gets shipped out. That's a lot of power. In US right here, when you look at the distribution, you know, which country contribute the most, it's certainly not this country right here. You know, we are in the bottom yellow part of this. China and Taiwan capture a big fraction of that. This tells us something. We are not that good at doing manufacturing. So this is not secret anymore. So everybody knows about that. To reach the grid parity, you know, PV is good, it's clean, but you have competing power generated by the fossil fuel, by the carbon, you know, by the coal, and by the natural gas. And the DOE Sunshot Initiative is really trying to bring down the cost of the PV system, the fully installed system. Going from in the past, let's look at the history. 2004, it's very expensive. And this curve is actually very aggressive. You're looking at 2010 also, or depending on the company, what technology you're talking about. This is roughly the number, $3.8 per watt, 3.5 type of range. Looking at where you can really bring this down to $1 per watt, eventually to reach the grid parity, make it very competitive without subsidy. You can also compete with the traditional energy sources. You need to do everything better, you know, including power electronics, the balance system, PV module, everything needs to be better. If you look at these, going from roughly around $3.5 type of range down to about $1 range, roughly the module needs to be around 50 cents per watt. And the other half is a balance of system power electronics. Along this line, there will be a lot of innovation needed to reach these goals. And in US right here, we have universities, national labs, startup companies, you know, doing a lot of creative research. What we are not that good at is when you come to the large scale manufacturing, go down to the low cost, how do you translate the initial innovation to the large scale manufacturing? 2010, DOE came out with a proposal called PVMI, Photovoltaic Manufacturing Initiative, asking center consortium type of idea to speed up the PV manufacturing. And there are two types of centers right here. One type is industry-led consortium. Well, it turned out the Samatech, this PVMC and SVTC, they won the two industry-led consortium. And they were also looking for university to lead a consortium. And Stanford and Berkeley team up. We spent quite a while preparing the proposals. At the end, we are the only university-led consortium winning $25 million for 5 years. The Samatech-led consortium is really focusing on CIGS, solar cells. And SVTC one is try to construct, the PV, pilot scale of line for silicon solar cells, try to reduce the cost of silicon. And at the outset, when we organized the Bay Area Photovoltaic Consortium, we are thinking this differently. We are not really focusing any particular absorber technology. We want to use the creativity from universities, try to work with industry to identify the right problems to work on. The objective for the university research, we want to perform the industry-relevant R&D to facilitate this high-volume PV manufacturing. We want to establish the problem, set up the problem, and the project with industry support. So we don't want to work in the isolation and vacuum. This consortium will also manage the open and comparative solicitations. So it's different from the usual university center we are familiar with. Usual university center, we bring in the funding. It's already determined which project this should go in. For this consortium, we bring this $25 million. We need to go through this open and competitive solicitation to find the right project with industry support to fund. That's how Sally mentioned, we recently selected 18 projects to fund going through this process. Certainly at the end, we want to speed up commercialization of cutting-edge PV technologies. These are all within the goals of BAPVC. Now the approach we are taking, now looking at the one of the most advanced solar cell technology based on CIGS. This is one of them. Roughly 12% efficiency also. You look at the distribution of the cost, involving materials, involving different components, involving processing. At the end, you come to the conclusion, you say to go down below 50 cents per watt, or significantly lower than that, you basically need to make everything better or cheaper, or and both. That's the conclusion we come up. It's not possible just looking at one isolated component and say if we do that better, this whole thing will happen. It doesn't happen this way. So when we set up this consortium, we want to look at, this is schematic of solar cells. There's a variation of that depending on what kind of solar cell technology you are talking about. If you look at a typical one, there will be encapsulation. Light comes in from the top, anti-refraction. You need the light to get into your solar cells as much as you can. And you also need a metal line contact as well. I didn't draw it right here. You might need transparent conducting electrode depending on the silicon solar cell or other solar cells you are working on. There's absorbers and junction formation, bottom contact, and the substrate. So we try to take the whole module approach to look at each component and both isolated component as well as how they couple together, work together, and try to look at this and say, yeah, we want to find projects at each areas so they can do better or cheaper. And we want to encourage the creativity in universities to look at these problems. And at the end, this is the whole module approach we see making sense to eventually push down to 50 cents per watt. Of course, in university, for us, it's not possible to do manufacturing. We can only design the right idea and prove it to the certain scale of device. Eventually, this needs to be transferred to the industry to help them to realize a below 50 cents per watt module. So in terms of time scale, it's also different from the usual research we conducted. We want this technology transfer to be faster. Typically, we are talking about 3 to 5 years to transfer this technology into industry. It does not mean in 3 to 5 years this is commercialized. It doesn't mean that. It means transfer to the industry. They can do further development and really push that into the real world. 50 cents per watt again is the number we are shooting for. We see this really exciting it's a really exciting opportunity once we can bring university researchers and industry people together, having a lot of interactions, coming back and forth, and there will be a lot of new ideas generated and can help the US PV manufacturing. And the initial member of this consortium, when we started, it was a Stanford and Berkeley led consortium and partnered with SLAC and LBNL and NREL. These are the consortium leadership. And Ali Javi and myself, we are co-lead the consortium. And John Banner, we hired recently from NREL. He was involved in the early proposal planning and helped writing the proposals. After the proposal was funded, he came to Stanford. Certainly, Steve has been involved right at the beginning and still very actively involved, try to help us to expand our industry program. And Dick Swanson, with many years experience in solar, is our chairman of executive board, and to help us to identify the right things to do as well. We already have a lot of resonance from the industry, and this is a list of the industry. They already signed up to be our industry members or about to sign up. And there's actually a long list other than this one. They show a strong interest. And you look at this whole list, you start to see it's actually the whole PV supply chain. And we not only need the companies having experience in the absorbers, we would like them to also have the experience in other components of the solar cells to help us to identify the right areas or problem to work on. So we have been through a process. We have RFP process, request for proposal, within Stanford and Berkeley. And about half of the funding will support the research in the internal institution, the initial 5 partners. And about half of the funding we will supply to outside and asking for good ideas to work on. This initial project, they are all within the 5 partner institutions. This project range from absorbers to metal contacts to many components of solar cells. So you will not be able to read this if you are sitting behind. I will give you some examples. What kind of project we are looking for. We have funded. Well, let me start by using my own research as an example. Starting from the absorbers, and there's many ideas working on absorbers. I personally, my research group has also looked at silicon, amorphous silicon, we have looked at chalcogenide solar cells. So within these consortiums, the idea of try to come up with technology in terms of in about 3 to 5 year time frame, transfer to industry. Here's one example, within this consortium. Try to look at silicon of very thin silicon solar cells. We are not talking about 100 micron anymore. We are talking about 10 microns or even thinner. Can you come up with the right structure when the light comes in and and having the right nanoscale photon management, whether it's a cone shape of structure or this a hollow structure engineer and the silicon, try to trap the sunlight inside. Eventually, only 10 micron or less can absorb all the above bandgap photons. And to demonstrate a decent efficiency as high as about, let's say, 20%, this will help reduce the solar cell cost, silicon solar cell cost, by quite a bit. So there's a lot of interesting idea really built on our past research. Let me give you an example, how this idea came about. In the past, we have been working on amorphous silicon, this type of nanocone. We know how to generate this nanocone. You see their separation around roughly 500 nanometer also. And diameter is a couple hundred nanometer. This is within the wavelength of the sunlight photons you care about. So this really allows you to manage the photon in a different way from the traditional solar cells. And looking at the nanocone and the amorphous silicon thin film about 1 micron thick, you see the nanocone after etching become black, completely black. All we figured this out is actually the anti-refraction. Refraction of light is caused by the refractive index difference between the air and your solar cells. Having this nanocone right here, the anti-refraction going from air into your nanocone goes through this anti-refractive index, goes through this gradual change. Compared to the flat film, there's a lot of refraction. This gradual refractive index really allow all the sunlight go into your solar cells and get absorbed completely. So based on this, we also extend this idea to a realistic solar cells. We take a substrate, we pattern a nanocone, and deposit the amorphous silicon materials on the top, forming these nanocone solar cells. Doing this way, you can couple the light, travel horizontally. Eventually, you only need very thin silicon, amorphous silicon in this case. I will come back to the crystalline silicon later. To absorb all the above bandgap photons. You can save materials, you can save processing. It's possible to also improve the efficiency as well because you concentrate the sunlight into this thin amorphous silicon. So we spent the last couple of years to figure out the light trapping effect, to make these solar cells starting from a tiny cone and deposit contact in amorphous silicon and eventually become a dome-shaped solar cells. We figured using this as an example, we figure out for the light absorption, these nanocone, nanodome do have significant enhancement. This is a flat film, absorb 65% of the light. This is a nanocone, nanodome, absorb 94% of the light. So we understand using photonic simulation. This is also the nature of this consortium. We want to encourage collaboration between different expertise of scientists. In this case, is a collaboration between my group and Professor Xianghui Fan right here, and using FDTD to demonstrate for the shorter wavelength, the absorption difference is really due to anti-refraction effect. For the nanocone, and you can have light coming in, looking at this intensity distribution, 400 nanometer light coming in and get absorbed completely. But for the longer wavelength range, and looking at 700 nanometer, we figure out light coming in and travel horizontally, get trapped inside this amorphous silicon, resulting this high absorption inside amorphous silicon. So, and this type of idea, over the years, we extend into the consortium, BUA-PVC consortium research. And what Xianghui is trying to simulate, we found a project by Professor Xianghui Fan using nanophotonic simulation to see whether it's possible to use very, very thin silicon to absorb all the above bandgap photon. Here's a schematic drawing. This is only 2 micron thick silicon. Typically, you're talking about you need 150 micron to absorb all the light. Now, this is only 2 micron. Using this double cone structure, the front cone light coming in from the top, this is the backside cone. They have different diameter. And the front cone allow you to get the sunlight in without reflection. The backside of the cone is when the light coming in and hitting onto the backside of the cone, it gets scattered. So you want to couple the light travel horizontally. Shanghai simulation showing using 2 micron thick film. This is a number you get out. In the case of A, this is about 35 milliamp per centimeter square of current you can generate it. It's very, very high. The world record solar cell based on silicon is roughly around a little bit over 40 milliamp per centimeter square also. So 35 is a very high number. So it's very attractive to use thin silicon to using nanoscale photon management to still realize nearly complete absorption of the sunlight photons above the band gaps. So based on these ideas and our past experience, within SPA-PVC, this is new development now in my group within this project. We are now making this about 12 micron thick silicon, very thin. You know, the silicon solar cell you're talking about, remind you again, is 150 micron. This is 10 times thinner. Now using this silicon, instead of brittle, it becomes flexible. You can bend this single crystal silicon. Now we are trying to playing with the nanoscale photon management on this type of silicon to try to really come back to make 20% efficiency solar cell using very thin silicon. So this is an example. Let me also highlight other examples as well within the consortium. This is from Professor Ali Jarvis' group in Berkeley. Ali is a co-director of the consortium. He's trying to make 3-5 solar cells on metallic foil. We know it's very hard to grow single crystal on metallic foil. For making 3-5 solar cell, you need a substrate. You need to do MBE, MOCVD growth of epitaxy. Ali is trying to do is taking advantage what's developed in nanotechnology, using this tiny nanoparticle as a catalyst to grow this nanowire nanopillar out in these arrays, and then he can peel off. This is now possible on stainless steel substrate. Here's one example. He grow. This is cadmium sulfide. It's not 3-5 yet. This is his past research. He tried to extend this approach into the 3-5. If you can grow the grain big enough, each of these nanopillar, nanowire is a single crystal. And also you try to manage the surface recombination, interfacial recombination right, it might be possible to realize a decent efficiency on a low-cost substrate. So we see if this idea really works. It's possible this type of idea can be transferred to the industry and going into the manufacturing with some modification. So we are looking at silicon, we are looking at 3-5, we are looking at different absorbers. Another example is Professor Clemens and Stacy Ban, Bruce Clemens and Stacy Ban, try to develop ZCTS solar cells. We know CIGS is solar cells having about 20% efficiency. It's a thin film solar cells, but indium is high cost, it's no abundant element. This research from a multiple research group tried to replace indium with zinc and tin. Zinc is divalent, tin is tetravalent, so indium is trivalent. Try to use 2 elements together to have the effect of indium. This consists of earth abundant materials. It can be low cost in the future. Excuse me. So in Bruce Clemens group and together with Stacy Ban, they already demonstrate pretty interesting efficiency. That's a 9.3% efficiency using a Grady band gap idea. Try to tune the materials using control the deposition right. We also see this type of an approach. You already demonstrate reasonable efficiency. If some resources can be allocated into this project and try to increase the efficiency further, let's say 15%, this can become very interesting for industry to take over to further develop. So with all this materials development, processing development, it's necessary within the consortium. We also need to have techniques to look at what's happening. We funded a project led by Mike Tony and Slack and Alberto Celeo at Stanford right here to develop advanced materials characterization technique, including using synchrotron X-ray to monitor during the process when you have a film formation, when you make a new materials, what's happening structurally, chemical bonding, and also looking at what's the defect formation using advanced optical spectroscopy such as absorption to look at the defects within the band gap. We see it's necessary to have people developing characterization technique, working closely with the teams developing new materials such as CCTS to work together. So, and in this area of advanced characterization, we seek the feedback from industry, and they keep telling us, for example, for thin film solar cells, what's the defect formation? We don't know enough. You can make a cell very small and with 18–20% efficiency, but once you do a larger scale, try to make a module, the efficiency drop below 10%. So what's happening? If you can have an answer and solution to this problem, this will have huge impact to the industry already. So we have a project right here led by Delia Miliron and Paul Alavasatos and Lawrence Berkeley Lab. They try to use the most advanced technique to look at the grain growth. And the thin film solar cells, a lot of processing is all about the grain growth. How do you control the growth? What's the chemical composition? What's the doping? What's the crystallinity? And Delia and Paul, it tries to take these nanoparticles using the most advanced technique available in the national lab, including transmission electron microscope, Raman, and the X-ray, to look at from this step to this large grain during the heating process, what's happening. Try to understand how the defect really form, how do you really create high quality, low cost thin film. Another project in these areas is based on the recent surprising discovery from Peidong Yang's group and UC Berkeley. Peidong was using cation exchange to make a solar cell. We know copper sulfide has been looked at 3 decades ago as a potential candidate of absorber to make solar cells. But it was given up because there's many problems identified related to these materials. Now 30 years later, Peidong picked up this project and looking at a different way. While looking at the history, the best copper sulfide solar cell using cadmium sulfide to form junction, you have open circuit voltage about 0.54 watt also, and a field factor is 70%, and this parameter just not attractive enough for solar cells. And through his research on nanowire, Peidong was making this cadmium sulfide using ion exchange, change a segment of the nanowire become a copper sulfide, now having a PN junction formation. And it's not for the manufacturing, but through this single nanostructure study forming these solar cells, he found something surprising. Now the open circuit voltage can reach 0.61 watt. It's very high. And the field factor is 80% compared to these parameters. Now you start to see a surprising result. Even single nanowire power conversion efficiency get up to 5%. Now this is a technique to really come back to look at materials system you're developing down to the single nanoscale grain to understand what's happening. In this case, 1 nanowire is 1 single crystals. You are forming a cadmium sulfide and copper sulfide junction. This is a single crystal interface. This creates really high performance for the solar cells. This type of information as a diagnostic tool can come back, feedback into your solar cell manufacturing and see whether you can promote a similar thing happening to improve your efficiency. So this approach is not only a solar cell, it's it's a diagnostic tool to understand what's happening, to feedback this information. We also look into a metallic line. We know a solar cell, you need a silver metal line to take out electricity. You need transparent conducting electrode to take out the electricity. And Professor Subramania and UC Berkeley is working on printing metal lines. And typically using the screen printing, you can get a silver line about 40 micron also. That's probably around the minimum you can get. Light comes in and go down into your solar cell. The silver line can block your sunlight. And is it possible to make the silver line very conducting, much narrower, allow more sunlight to pass through? VVAX group is really developing new type of processing, moving away from silver and try to make the line width narrower. And these type of idea, if successful, can be directly transferred into the industry to combine with the existing solar cells. So I have another project going in the group related to a consortium. We have been also trying to develop transparent conducting electrode, which can be combined with the solar cells. So there's a process called electrospinning. This is a polymer and a needle, and when you apply a voltage, you charge up this polymer, the strong electric field will extrude out this fiber very, very fast. This type of idea, when I look at this several years ago, I said this might be possible for us to make a nanowire transparent electrode like this with metallic mesh, cover large areas. And if you can make metallic nanowire this way, it's possible to generate a high performance transparent conducting electrode. Well, let me show you a video just for fun, how fast this process can be. What you see right here is a needle. With alligator clip right here, apply a high voltage, now electrospin out this fiber. You see the electrospinning speed is very fast. One needle can shoot out this fiber in the speed of 1 kilometer per second. It's very, very fast and covering a large area surface. So this type of process allows us to make a nanowire mesh like this, metallic wire like copper. And also, based on this idea, extending to more of the metals, now you are really seeing a really great performance. This is transmittance versus the shear resistance. For copper, nanowire, nanofiber, this you get down to more than 90% transmittance, only a few ohm per square. Really, really great performance. You can do silver, you can do gold and aluminum. So for touch screen device and your cell phone, and this type of transparent electrode can be also a great candidate. Let me just show you something fun as well. This type of transparent electrode is also flexible. Here is a nanowire mesh depositing onto a plastic substrate, so you can bend this substrate. And we make a touch screen device out of this type of nanowires. You can write on it, and it show up on the screen what you are writing. So this provides a really interesting solution for also flexible solar cells because now the transparent electrode is flexible. So we also found another project. Mark Braun-Gusma, a photonic expert, is developing idea other than just a simple nanowire mesh. He come up with this very interesting percolating patterns, having a quite dramatic effect. If you put this type of metallic pattern, they can function as an electrode onto a light absorbing material surface. This just make it black. It has a really good anti-reflection as well as the the nanoplasmonic effect right there. So with all this development, not in a traditional sense, you see in the solar cell industry, you have this nanowire transparent electrode, you have other processing that's different from the traditional solar cells. Mike McGee is combining many different things together. You don't do it in a traditional way. The organic solar cell with inorganic solar cells to form a tandem cells, so to have different band gap, having the process compatibility, incorporating this new type of transparent conducting electrode. So we have another project as well in this area. So reliability is very important. And many our industry members ask, whether we can help them to identify how solar cells fail and how do we address those problems. And Rainer Dauska is an expert in these areas. He is really looking at how the solar cell fail under the light, under the atmosphere environment. You have water, you have oxygen around. And also the mechanical stress once you bang onto your solar cells, what might be happening. So Rainer is putting out a program within the consortium to adjust the reliability. We understand we also need to look into new type of materials, try to do a better encapsulation to increase the lifetime of the solar cell to prevent water, oxygen to diffuse in. And there's a team within the consortium, Richard Sigerman and Jeff Urban and Lawrence Berkeley Lab, try to look at polymer and nanoparticle composite, arrange them in an interesting way, such as right here. Try to capture the moisture, try to prevent the moisture diffusion in. And having this interesting property eventually results in much better encapsulation. Now let me spend a few slides, to look at the whole consortium structure. With this initial project identified, this is really within the operation. It's very healthy. We have the industry board right here. And they contribute a lot of ideas. What are the areas we should look into? What's missing in the PV manufacturing? And consortium leadership, basically 4 of us, taking this idea, and we certainly consult with the DOE. We have the executive board right there. We look for the project having the industry impact to fund. And the 18 projects that come from, we call internal program, because these are the 5 initial institutions. We are now in the process and asking for the ideas from the outside institution also to fund, complementary to the project in the internal program. I see some of the industry people sitting in the audience right here. And industry has a very strong motivation to come in. They have been enjoying quite a bit when interacting with the university researchers. They see they can have access to the leading university scientists. This is attractive. We also have the semi-annual workshops to bring everybody together to talk about what's happening. They reveal the best proposals. They certainly engage a lot as well in the research progress. They also contribute certain funding into the $25 million DOE already put in. So it will be a really nice leverage between a government agency and the industry. And they also have the chances to do a technology commercialization generated within this consortium. So with this, we already seen, the Bay Area Photovoltaic Consortium really provide a vibrant forum for the interaction between industry and academia experts. And we have been running a mechanism of identify the right scope of the research to facilitate the PV manufacturing in the US. And we want to find and fund the best university teams to develop relevant technology. With that, I'll stop right here. I will be happy to answer any questions you have about the PV consortiums or particular technologies. Thank you for your attention. In the back, right there.
Twin Creek Technologies has their 20 nanometer thin silicon, and they say that the cost is something like around 5 cents per wafer. So what's the beef creating all this technology when you have a material that's so cheap? You have other problems, attendant problems like processing costs and handling materials that are so thin. So what? And even Twin Creeks is having trouble getting it up to 20%. They have a heterojunction design. I think they've tapped out at around 18.8.
So you mean it's not 20 nanometer? You mean 20 micron?
Yes. Here I see
20 micron
you're pushing 3. You know, I spoke to Harry Atwater. He said he is a 3% too, but he says maybe around 4% efficiency. No, you need high efficiency, not low efficiency.
Yes, absolutely true.
You're failing to accomplish what Steve Chu really wants. He wants the balance of systems. The only way you accomplish that is 20 to 25% efficiency. Who cares if you have a 3%, 4%, 6%, all these other thin films? All these VCs have dumped $5 and $6 billion, and it's all down the toilet.
So what's your question?
Why are you pushing with these other ones? It seems like you should be pushing the thin crystalline. I think you get more bang for the buck. Your first starting slides where it sound like you're on.
So I don't quite get your question. So let me repeat. What's your question? You are saying if you go down to very thin silicon, you cannot generate the high efficiency. Is that your question?
Why do you assume that's the question and answer it?
Yes, I assume that's the question. I don't think it's a done deal. It's a 10 micron will not generate high enough efficiency. That's not a done deal. So that's why it needs university researchers to look at this problem. I agree with you. When you go down to 10 micron, the processing you need to come out is very different. Mechanically, they are very different. It's not a rigid wafer anymore. How do you handle those materials is different. But I don't think it's already this conclusion saying you cannot handle this wafer anymore. That's exactly the type of project I think BAPVC need to look at. What if we come up with an idea, approach, a processing, we can get the whole thing done? That will generate huge impact.
Okay, another question from somebody else. Okay, how about back over there? Yeah.
You say that you are looking into 50 cents per watt in 3-5 years. Where are you today at your best effort? What is your today's price?
Can you repeat your question?
The question
you are looking in.
Yeah,
If you can.
That he's asking, where are you? And you want to go to 50 cents per watt, and where are you today? Where's the best sell today?
So let's see. The best thin film we are talking about around 75 cents per watt also. Silicon more expensive, about $1. That's a starting point. But as I said at the beginning, within consortium, university does not do manufacturing. To give you a cell, we can sell to you is 50 cents or 75 cents. We are generating technology, transfer to the industry to help them reach this goal.
So the whole story is about 25% cost decrease, right?
25% or more, depending on the technology, yes.
Or 100, it's 50 to 100% decrease in cost. If 75 is the best where we are today, and
Right.
it's $1 for silicon, and you
Right.
want to go to 50.
That's
So
right.
50 to 100% reduction in cost.
Right.
Yeah.
Yes,
Okay.
yes.
All right, more questions. Okay, do we have any students in the audience? Oh, everyone else is going to get a chance. Students, okay, right there. Great.
First, thank you so much for coming. I was wondering if there were the first of its kind in terms of organizations that promote PV innovation, on a local scale, or if similar organizations have existed in the past, and whether or not it's the first of its kind, or if others have existed in the past, whether this has been based on those or this is really innovative.
So a similar center like this, try to look at concentrate so much resources on PV. This is not the first time. And PV has been looked at, by university centers, by VCs, investors, sitting right here, like these two gentlemen. I think this BAPVC is new in a sense. It brings the industry and university researchers so closely to interact. It not only bringing just one university, bringing multiple universities, looking at our industry members, multiple companies all sitting in the same room, talking about relevant things. And we also feel surprised how much industry members are willing to say. They actually say a lot more than we expect. So that's the value I think we bring in.
Okay, how about Keith? Yeah.
So there's a lot of single projects looking at single aspects of it. Within the consortium, is there anything looking to put the different parts together?
Yes, that's a really good question. You see, so far is individual component. We actually are having a few mechanisms to put all the things together. One is through individual principal investigators in the consortium. Second is through working with industry. If anything we generated looking promising to them, and we'll work with them closely, try to put this individual component in their state-of-the-art solar cells.
Okay, all right. Any more students? Okay, maybe we'll go back into the back there, and then we'll come up to the front. Yeah.
Can you share your vision for the applications of PV? Because with some of these new technologies, it sounds like you can go beyond utility scale PV, like these big solar farms, and actually deploy PV on vehicles and clothing and embedded in building materials.
Yes, I think that's absolutely true. When we set up this big goal of $1 per watt in the installed system, that's utility scale. We are talking about 50 cents per watt in the module. At the same time, some of these technology, flexible solar cell, for example, this can be put into environment. That's not necessary. The utility can be combined with cars, can be combined with the indoor applications. We actually have the industry members that are interested in the part of the technology which is not a utility scale. It's more of in the low light condition. What can you come up, for those applications? I think yes, these will open up other opportunities as well.
Okay, all right. Okay, we'll go here, and then we'll come over here. Yeah.
So you've got 18 projects from the academic community. What's the process, and when are the sort of industry projects going to be reviewed and worked on?
So this consortium only fund university and national lab research. We don't fund. Are you saying we are funding industry research? No, we are not funding.
Industry players around here can't kind of get into it except as to help university research.
So Steve is right here. So industry researchers that are interested in this consortium, our doors are open all the time. You can come in to talk to us. And we have twice review meeting each year for the industry people to come. This other possible time, industry people can come as well by appointment basis.
Okay, all right, okay, how about over here? Yep.
Yeah, so I was struck by a little bit of a parallel with the old Center for Integrated Systems that was started, what, 30 years ago, something like that. And I'm wondering if you had compared notes with those folks at all.
All the time.
Oh, good.
Yes, that's a model. You know, we try to learn. You know, CIS has been so successful right here. You know, for Stanford, for the Valley, this is the model we are trying to learn. You know, we are talking about this every time. Steve and I, yeah, we talk about that. Yeah.
Okay, how about down here?
Manufacturing processes. You mentioned the absorber, and that's the target for the absorber. How about all the rest of the 17 projects? I guess it's 17. And is anybody focusing on manufacturing processes?
You know, I would say only on the individual components process, such as printing the silver metal lines. No, not yet. The whole manufacturing, no, not yet.
That's where you really drive down costs.
Yes, I think we would love to get input from industry, from you. You know, if you tell us this is an area we should look at, we will look at. Yeah.
Right. You need some partners in that.
Yes. Yeah.
Okay, I've got a question for you. So what is the model eventually? So you guys, you know, come up with some good idea. How then does industry start investing? And, you know, what's the procedure to go to that next step? Have you thought about that? Have you talked with your industry partners about it? And
I would say the conversation are starting. You know, what's the best mechanism to have this transfer happening? One thing for sure, our data, our results needs to look interesting to them first. Yeah, we are still talking about that. Yeah, this mechanism.
okay, all right. Any other questions? Yeah, right there. Yeah.
I'm very impressed that you got this brilliant idea of starting the PVC and then make it happen. So can you just share how did you get this idea at the beginning, and then what was the challenge you faced? It seems like it's magic to get this $25 million. And I just want to know what was the main challenge.
Let's see. So you are asking, you know, how do we come up with the idea? We want to do a consortium. How do we organize the team? I think the first thing is you find the right guy to work with you. That's why. Then everything will flow. Well, let's talk offline. It takes much longer to explain.
Okay, all right. Well, with that note, anyway, thank you so much.
Yeah, thank you.
For more, please visit us at stanford.edu.